In Chapter 3, which we just wrapped up, we talked about ionic compounds. And so in Chapter 12, we're going to move on and talk about the other type of chemical compounds you can have, which are called covalent compounds. These are some models we'll be looking at during the lecture on the chapter. In a covalent compound, the key difference is that the atoms are held together because they share electrons, rather than in ionic compounds where one atom gives electrons to another. So we'll start out in the chapter and talk about the nature of covalent bonding. How is it that sharing electrons actually causes two atoms to stick together? It's pretty obvious in ionic compounds. Ions stay together because they have opposite charges. But in covalent compounds, the atoms don't have positive and negative charges because they haven't actually exchanged electrons. So how is it that sharing a pair of electrons will actually keep those two atoms together? We'll talk about that. We'll learn how to draw pictures of molecules. I'll take you through a procedure where you'll be able to figure out what the attachments are between the various atoms. How do we hook the atoms together? What shape will the molecules have? It turns out that the shape is a very important thing. Chemical properties are greatly dependent on the shapes of molecules, the angles that the atoms form with each other. By the time we finish up Chapter 12, we'll have completed our first unit, and after that, of course, will be our first midterm, covering Chapters 1 and 8, 2, 11, and 3, and now, of course, Chapter 12. So, let's go ahead and get started and learn all about covalent compounds. In Chapter 3, we focused on ionic bonding. And in ionic bonding, one atom simply gives an electron to another atom. For example, we took a look at lithium reacting with fluorine. And we found that lithium would give one of its electrons to fluorine. That would give lithium a full first energy level, making it isoelectronic with helium. And that would give fluorine a filled second energy level, making it isoelectronic with neon. So once that happens, now both of these atoms have now become ions. We have a positive lithium ion and a negative fluoride ion, and then the two ions simply come together to form an ionic compound, in this case, lithium fluoride. In Chapter 12, we're going to talk about the other type of bonding you can have, which is covalent bonding. And covalent basically means sharing valence electrons. Let's take a look at a simple example of two atoms sharing electrons, and that would be hydrogen. Each hydrogen atom has only a single electron. Each hydrogen atom is unsatisfied with the number of electrons it has. They would like to have two electrons so they could look like helium. The hydrogen on the left would love to steal the electron from the one on the right, and vice versa. But nonmetals cannot take electrons from each other. It's the nature of metals to want to lose electrons, and it's the nature of nonmetals to want to gain. When you put a metal and a nonmetal together, that's great. The metal wants to lose, the nonmetal wants to gain. When we put two nonmetals together, they both want to take electrons, and that's just not going to happen. So instead, they have to share electrons. We can pool those two electrons together. Now, mathematically, for those of you that are interested in quantum mechanics, which I'm guessing is very few of you, but each of these circles here represents a 1s orbital in the hydrogen atom. And you may remember from Chapter 11, the reason we know that it's a spherical shape is because Schrödinger's mathematical equations, if you simply graph the mathematical function for an s orbital, it looks like a ball. Now, just like in math, if you take two equations in algebra and you add them together, you can graph the result. If we take the equation for this hydrogen atom and the one for this hydrogen atom, we simply add together the x's, the y's, the z's, or whatever, and then we graph that result. It ends up sort of having this football shape. Now the electrons, instead of being separated one on each hydrogen atom, they're mainly flying around in between the two nuclei. With an ionic compound, it's real obvious why the ions are attracted to each other. It's because they have opposite charges. The same thing essentially happens in a covalent bond. When those electrons move into the middle between the two protons, now the positive charge of the proton is attracted to that cloud of negative charge in the middle, and so those two protons are pulled together. That attraction is a covalent bond. Essentially, ionic and covalent bonds have one key thing in common, and that is they both are due to positive and negative charges attracting each other. In an ionic compound, one side is positive, the other is negative. In a covalent compound, the two ends of the molecule are positive, but the center is negative. Net result, we still have a strong attraction between positive and negative charges. Now, we're not going to draw anything quite this complicated for the remainder of our molecules in Chapter 12. An easier way to look at two hydrogen atoms coming together is just to use those dot diagrams that we talked about previously. You can imagine that the two hydrogen atoms simply come together and they pool their dots, or their two single electrons, and they make them into a pair of electrons. One of the analogies I like to give my students is to think of these electrons as like a fence between two atoms. It's been windy lately, and sometimes the wind comes up and your fence gets knocked down. And ideally, if your fence gets knocked down, the neighbor behind you and you will split the money, and you will join together to build that fence. So you're each essentially putting in half of the fence. And that's essentially what the two hydrogen atoms are doing here. They're each donating half of that pair of electrons. In the end, each hydrogen went from owning one electron all by itself to owning half of a pair. If two neighbors get together and build a fence, they theoretically each only own half of that fence, but they have a fully functional fence. Ask yourself this: what would be better? For you to build a fence halfway across your yard, but it's all yours? Or for you and your neighbor to get together and build an entire fence, but you only owned half of it? And of course, half a fence isn't going to do you much good. You build a fence halfway across your yard, you let your dog out in the morning, and the dog is gone. So it's much better to be the half owner of a pair of electrons than the sole owner of a single electron. When this hydrogen atom looks out the window in the morning, it sees that pair of electrons and says, "Man, I feel just like helium today." And the other hydrogen is the same. So having a pair of electrons is much better than having that single electron. This method of showing the molecule is called a Lewis structure. Lewis is the guy that gave us the Lewis dot diagram for individual atoms. And when we do the same kind of drawing for a molecule, it's called a Lewis structure. There's a simplified version of this that's commonly used, and that is we can take any pair of electrons that's shared between two atoms and just illustrate it as a line. So anytime you see a line connecting two atoms, that means that that's a pair of electrons. That's a covalent bond. This particular diagram is known as a ball and stick drawing. In the chemistry lab, if we were there this week and doing experiment number 16, you would be building molecules out of a model kit that we have where each atom is a round wooden ball and we have little wooden sticks to connect them with, thus the ball and stick kind of drawing. The simplest but least informative way of showing a molecule is just to show the molecular formula, H2. That doesn't tell us a lot about the molecule. The Lewis structure or the ball and stick drawing are much more informative because it shows us how the atoms are connected together, how many bonds there are between each atom. And trust me, the molecules are going to get bigger and more complicated pretty soon. They won't all be as simple as hydrogen. By the time we get through this chapter, the main thing you're going to be able to have to do is to take a formula like this. I will give you a chemical formula, and then I will ask you to construct a ball and stick diagram, and from that, a Lewis structure. As we've talked about in previous chapters, elements in a group tend to have similar properties, and that means that the bonding that elements do will be very similar within a group. So let's take a look at the types of bonding that the elements want to do in each of the groups on the periodic table. We are going to only focus on those groups which have nonmetals. That's mainly groups 7, 6, 5, and 4. There is one nonmetal in group 3 and of course hydrogen in group 1, but the majority of nonmetals fall in these 4 groups. I'm starting with group 7 and working my way back because 7 is the simplest. They get more complicated as we go along. Let's allow fluorine to represent our group 7 elements. Because it's in group 7, each fluorine has 7 valence electrons, 3 pairs and 1 single. In general, what an atom wants to do is to find a partner for any single electrons that it has. Atoms like to hold on to any pairs of electrons they've got, but they want to find a partner for their single electron. The rule of thumb is for every electron an atom needs, it will form a bond. These fluorine atoms each need one more electron, so they want to form one bond. They will share a pair of electrons, and they will keep their 3 pairs of electrons they had to start with to themselves. The electrons that are shared between 2 atoms are logically called bonding electrons because they form the covalent bond. And equally logically, these electrons that belong to just a single atom are called non-bonding electrons since they're not involved in bonding. They're sometimes also called lone pairs of electrons because they belong to a single atom. This is another way of drawing the Lewis structure. So we can show the Lewis structure with all dots, but it's also commonly done that we take any bonding pairs of electrons and simply turn them into these lines or sticks. So both of these would be considered the Lewis structure of the fluorine molecule. It shows the non-bonding electrons as this bond and each of the pairs of non-bonding electrons. To get to the ball and stick diagram, all you do is eliminate the non-bonding electrons. That doesn't mean they're gone, it just means we're not showing them. This is a simplified picture. If a chemist were to see this ball and stick drawing, the chemist would immediately know, oh, there have to be 6 more dots on each fluorine in order to get that octet. If any of you have ever gone to look at model homes, when you go into a model home community, they hand you a little packet with floor plans for the houses. And the floor plans are very basic. They don't show much detail, just sort of the general layout of the house. It doesn't show the electrical outlets or the faucets or any of those other details. You still get those, it just doesn't show them because it would be too complicated. When the builder is constructing your home, they use blueprints, which is a very detailed drawing. So the Lewis structure is sort of like the blueprint of the molecule. It's got every detail in there. The ball and stick drawing is like the little floor plans that they hand potential customers when they come in to look at the homes. It has the basic overview of the house, so you know essentially how it's laid out. You don't really need to see every little detail in there to know what the house is going to be like. And finally, of course, we can just write the formula or the molecular formula for the fluorine molecule, which is simply F2. Moving over to group 6, let's take a look at oxygen. We're just going to use the top members of the groups representatively, and we can assume that in most cases the elements below them in the group will behave in a similar way. Not always exactly the same, but for now, to keep things less complicated, we will just assume that that will be the case. In group 6, the oxygen has 6 valence electrons, and as we learned in chapter 3, that would be 2 pairs and 2 single electrons. Because each oxygen needs 2 more electrons to achieve an octet, they're going to want to form 2 bonds. Each oxygen then is going to put its 2 single electrons into the middle, and it's going to form what's known as a double bond. So this is a single bond between the 2 fluorine atoms. We have a double bond between the 2 oxygens. you're probably surmising that a double bond must be stronger than a single bond, and it is. A double bond is much stronger. It's not twice as strong, but it's close to that. So oxygen atoms are held together much more tightly than fluorine atoms. That's a reason that fluorine molecules are much more reactive than oxygen. Fluorine is a very dangerous material. In order for fluorine to react with another element, the two fluorine atoms must first break apart, and with only a single bond, that's not hard to do. For two oxygen atoms to attack some other substance, we have to break that double bond, and that's more difficult. And that's lucky for us, because oxygen would be a very dangerous substance if it was easier for those atoms to get apart. But that double bond keeps oxygen just stable enough that it works out perfectly for us. We can do that alternative version of our Lewis structure, where we take the 4 shared electrons and simply make 2 lines. Each of those lines, of course, is a covalent bond, which means it is a pair of electrons. If we want to do the ball and stick drawing, we'll just erase, we'll make those non-bonding electrons invisible. They're still there. A chemist knows they're there. They can see them in their mind. But we're just going to show now how the atoms are connected together. And then again, the least informative way of writing it is just O2. So the subscript 2, of course, tells us how many atoms. That 2 is not how many bonds there are. It says there are 2 atoms of fluorine. There are 2 atoms of oxygen. Moving on to group 5, we'll look at nitrogen as our representative. And in group 5, of course, they have 5 valence electrons. That means 1 pair and 3 singles. So each nitrogen, it needs 3 more electrons. They're going to want to form 3 bonds by joining their 3 electrons from each atom together. So each nitrogen will put those 3 single electrons in the middle, and we will now form what's known as a triple bond. Triple bonds are very strong, which is why nitrogen is an extremely unreactive element. Plants need nitrogen to live, and the atmosphere is full of it. It's 78% nitrogen in the air. You would think the plants could just suck out nitrogen from the air, but for the most part, they can't do it. Because to make use of the nitrogen, they have to break that triple bond, and that is very difficult to do. For most plants, then, we have to feed them a fertilizer that has individual nitrogen atoms in it rather than nitrogen molecules. To make our other version of the Lewis structure, we'll turn those 6 shared electrons into 3 covalent bonds, or 3 lines. For our ball and stick drawing, we'll simply make those non-bonding pairs invisible and just show our triple bond. Or, again, the simplest way to do it is just N2, because there are 2 atoms of nitrogen. Finally, we get over to group 4. You may remember that poor old carbon back in chapter 3 was unable to form an ion because that was just too many electrons to gain or lose. So we said, well, when we get to carbon, we'll share electrons. The carbon atoms each need 4 more electrons, so they want to form 4 bonds. And here's more bad news for carbon. The maximum number of electrons that carbon can put into the middle is 3. This electron over here is in an orbital that points in the opposite direction. It cannot be bent around into the middle. So it looks like poor carbon is going to lose out again. Is there nothing we can do to give poor carbon an octet? Well, there is. All we have to do is simply bring in more atoms. There's no rule that says you can only have 2 atoms in a molecule. If that were true, there wouldn't be very many molecules. Chemistry would be a heck of a lot easier. So we could bring in something else. Ideally, we want to bring in someone that could add 1 electron to each side there and make the carbon have an octet. A good choice would be hydrogen. If a hydrogen atom brings in its 1 electron and another on the other side, now the carbon has 2 here and 6 here. It's got its octet. This carbon has 2 and 6. It has an octet. And of course, hydrogen has its lovely duet to make it look like helium. This particular molecule is known as acetylene. This is the stuff that welders use in their flames to do welding. It's called an acetylene torch. This stuff burns very well. We can turn this into the ball and stick diagram, and because all of the electrons in this case are bonding electrons, and that's virtually always true for carbon, and it is always true for hydrogen. Hydrogen never has leftover non-bonding electrons. It only can have one bond. And carbon atoms, in all but very rare cases, its 8 electrons are always in the form of 4 bonds. We can then make, of course, the simple molecular formula of C2H2. It tells us the molecule contains 2 atoms of carbon and 2 atoms of hydrogen. We now know that elements in group 7 need 1 more electron, so they like to form 1 bond. The elements in group 6 need 2 more electrons. They want to form 2 bonds. If you're in group 5, you need 3 more electrons. You form 3 bonds. And in group 4, they need 4 more electrons, so they want to form 4 bonds. And I keep using the word want. That's going to be very important later on. When it comes to elements, they have wants and needs, just like people do. Our needs are things like food and shelter and oxygen and water, things like that. Our wants are new cars, big screen televisions, that type of thing. So for an element, its need is to get an octet. Each element needs that octet. When you're drawing pictures of molecules in a little while, that is your number 1 requirement. You must give the atoms an octet, unless, of course, it's hydrogen. Hydrogen only gets a duet, but everybody else should have an octet. Now, there are exceptions to that rule, but the good news is not in Chem 3A. When you get onto general chemistry, you will talk about molecules that don't obey the octet rule. I guess that's why we don't call it the octet law, because there are exceptions to it. But to keep things more straightforward, Chemistry 3A is your beginning chemistry class, and so we don't want to complicate things more than we have to. Well, as far as you're concerned, whenever you're drawing a Lewis structure, other than hydrogen, every atom, when you're done, must have an octet. So the combination of non-bonding and bonding electrons has to add up to 8. It turns out that there's more than one way for an atom to get the number of bonds at once. I'm going to reverse the order this time, and we're going to start with group 4 and work our way across, because group 4 is the most interesting one. We'll let carbon represent group 4. So everybody in group 4, as we've decided, wants to form 4 bonds, but it turns out there's more than one way to accomplish that. One possibility would be to form 4 single bonds. As long as the total number of bonds adds up to 4, carbon will be satisfied. Another possibility would be 2 double bonds. You might imagine if carbon had 4 single bonds, perhaps hydrogen would be a good partner, since hydrogen wants single bonds. A carbon that wanted double bonds, perhaps oxygen would be a good partner, because oxygen is capable of forming double bonds. Carbon can also form a single and a triple. 1 plus 3, of course, still adds up to 4. We might imagine putting a hydrogen over here and a nitrogen over here, just to make sure each atom had the number of bonds it wanted to have. And there's a 4th possibility, and before you say it, it's not a quadruple bond. You can't put 4 lines on one side. We talked about that just a couple of minutes ago. The other possibility is a double bond and 2 single bonds, as long as they add up to 4. So 1 plus 1 plus 2, 1 plus 3, 2 plus 2, or 1 plus 1 plus 1 plus 1. Carbon is a very versatile element. About 90% of all known chemical compounds are carbon compounds. Carbon can bond in lots of different ways, and it can bond with just about every other element. Carbon is actually the only element that will bond with itself in an unlimited fashion. You can hook thousands of carbon atoms in a chain. No other element is able to do that. That's the reason Carbon is the backbone of living things. We talk about ourselves as being carbon-based life forms here on Earth because carbon makes a great backbone for molecules since it can bond to so many different things in so many different ways. If we go on to group 5 and look at nitrogen, we learned that nitrogen wanted to form 3 bonds because it had 1 non-bonding pair and 3 single dots. So it wants to get partners for those 3 dots, but keep the non-bonding pair to itself. Another way you can get 3 total bonds is a single and a double, and the third possibility is just a triple bond. In each of these cases, nitrogen has its octet. 2, 2, 2, and 2. 2, 2, and 4, or 2 and 6. Those all add up to 8 electrons, so nitrogen's perfectly happy to bond in any one of these ways. And that makes nitrogen also a very versatile element. There's a lot of nitrogen in living things. Things like DNA molecules have lots of nitrogen in them and lots of carbon because nitrogen is also very versatile in the way it can bond with other atoms. If we take a look at group 6, with oxygen, oxygen had 2 pairs and 2 single electrons, so oxygen wants to form 2 bonds. And it can do it 2 different ways. You can have 2 single bonds, or oxygen can form a double bond. Not as flexible as, say, nitrogen and carbon, but still it can at least bond in 2 different ways. When you get to group 7, not so versatile. Fluorine has 3 pairs of electrons to itself already and just 1 single dot, so fluorine only wants to form 1 bond. Now again, we're talking about once. Can these atoms ever form a different number of bonds than what we've shown here? And the answer is yes, with one exception. There's one atom in this table that will not do anything different, and that is our buddy fluorine. Fluorine is the most powerful element on the periodic table. Being in the upper right-hand corner makes it the strongest element of all in terms of its ability to hold on to electrons. If another atom comes along and says, hey, fluorine, how about sharing another electron? Fluorine says, hell no, not going to happen. So fluorine refuses to form more than 1 bond. Now, chlorine, bromine, and iodine underneath fluorine, they only want to form 1 bond, but they can actually form more. You'll see that in some of the examples we do in the lecture here and the molecules you'll be doing in the lab. Now it's time to put all of this together and start drawing Lewis structures of molecules. This table here will give you sort of a guideline. Basically, this table tells you the wants of each atom. That carbon atoms want 4 bonds, nitrogen atoms want 3, oxygen wants 2, and fluorine wants only 1. You will see in some of the examples we do that, say, carbon, nitrogen, and oxygen will not always get what they want. They will always get what they need. They will always get their octet. Fluorine is one atom that will never change. It will always have 1 bond and 3 non-bonding pairs of electrons because it's the strongest element on the table. It refuses to form more than 1 bond. The other atom that also refuses to form more than 1 bond is hydrogen, and that's simply because hydrogen can't. It's incapable of that. To form a bond, you need an orbital in which to put that bond. And hydrogen, being in the first period and the first energy level, only has 1 orbital. So for hydrogen, it's physically impossible to form more than 1 bond. Fluorine simply says, I refuse to form more than 1 bond. These other elements, they can do different things. You may see an oxygen with 1 bond. You may see an oxygen with 3 bonds. Nitrogen might have 4. Carbon might have 3. It's not common, but it does happen frequently, and I don't want you to worry about that. So when you're drawing a structure and you're thinking, man, my nitrogen's got 4 bonds, am I in trouble? Well, not necessarily. As long as the nitrogen has its octet, that's the key. When you do a Lewis structure, your ultimate goal is to satisfy both the wants and the needs. You must get the octet, but you would like to give the atom the right number of bonds. So if you can do both of those, I want you to do them both. To be 100% correct in a problem. If it's possible to get both the octet and the desired number of bonds, do that. But if it's only possible to get the octet and the bonds can't work out, then don't worry. And I'll be showing you some examples of exactly that here in just a moment. So let's go on now and see how do we actually put together the Lewis structure for a molecule. I have a 4-step process, and I can promise you if you will follow this process religiously, you will get the right answer. I know from years of experience, every time a student gets the wrong answer, it's because they didn't follow the steps. So make sure you follow these steps very carefully. Step number 1 is to draw the skeleton of the molecule. All that means is basically tell me who's connected to whom. If I give you 2 carbons, 4 hydrogens, and an oxygen atom, you need to come up with a logical way those atoms could be connected to one another. You may come up with a skeleton that ends up just not working, and that often happens. If you do that, if your skeleton won't work out, don't worry about it, just try a different arrangement of the atoms. Our second step is to count the valence electrons, and that's easy to do. If you say you had 2 carbon atoms in a molecule, well, carbons in group 4, they each have 4 valence electrons. If you had a fluorine atom in your molecule, oh, that's in group 7, that's another 7. You simply add all those up. You want to figure out how many electrons do I have to work with when I draw my molecule. Once you've counted those, you're going to have to make sure you add all the remaining electrons that you didn't use in the skeleton. When you draw the skeleton, as you'll see in a moment, you only use single bonds to hook the atoms together, which means you're going to use some of your valence electrons to hook the atoms together in the skeleton. Once you've calculated how many total you have, when you go to step 3, however many electrons have not been used yet, you need to add those to the molecule as dots. So you're going to add them as non-bonding pairs of electrons since you've already done the bonding electrons. The number 1 place that students mess up is counting these electrons. They will count the electrons and come up with 16, and then they'll raise their hand for me to check their answer. I come and look at it. I see 14 electrons, or I see 18. In class, I simply walk by the student, I point to him and say, did you count the electrons? And they'll hear me say that constantly. And what I really mean is, you didn't count the electrons. If you don't count them correctly, you are not going to be able to get the structure done. Our 4th step is to make multiple bonds if needed, and that is super important, as you're going to see in a moment. That means double or triple bonds. Sometimes when you get done putting all the electrons in step 3, there are still some atoms that don't have their octet yet. And so by making double or triple bonds, we can get them their octet. And I'm going to show you how that works in a moment. Turns out that students love double and triple bonds, and so they tend to put them in even when they are not needed. I've had students that have an atom and a molecule, and I count 16 electrons around that atom. It's called the octet rule for a reason. We only want 8. We don't want 10 or 12 or 14 or 16. More isn't better. An atom wants exactly 8, no more, no less. When you get to the end of step 3 and you've added the rest of your electrons that were available, if everybody has their octet, you're done. You want to stop right there. If, however, there's an atom or more than one atom that have less than 8 electrons, then and only then will you go to step 4. That's why I put if needed in really big type. Don't do it if you don't need to. Let's go ahead now and work through some problems so I can show you how to use that 4-step process efficiently. The first step, as you recall, is to come up with a skeleton for the molecule. The first thing you have to decide is where are the atoms going to go? A good starting point is to pick whichever atom in the molecule needs the most bonds and make that the center. That, of course, is always going to be carbon. Carbon wants to form 4 bonds, so we normally would put carbon in the middle. Hydrogen, because it can only form 1 bond, will go on the outside,
And oxygen, of course, can go either way. Let's take a look back again at that table we had a moment ago. If you look at the 4 different ways that carbon can bond, in each case carbon has at least 2 partners. It has 4 here, 2 here, 2 here, and 3 here. So carbon is not going to be on the end of a molecule, because if it were on the end, it would need a quadruple bond with its partner, and that's not going to happen. Nitrogen can go either way. These 2 forms of nitrogen would be in the interior of the molecule, but the triple bonded nitrogen would go on the end. So nitrogen can go in the middle or the end. Same is true with oxygen. With 2 single bonds, oxygen can be in the inside of the molecule. With a double bond, it goes on the outside. Fluorine, of course, always goes on the end. It's always on the outside, just like hydrogen. So let's see if we can come up with a reasonable skeleton. Since carbon needs to be in the middle and hydrogen on the end, this would seem to be a reasonable approach. Now you can come up with other skeletons. You might say try to put the hydrogen over on the end of the oxygen here. That wouldn't violate any rules, but what you're going to find at the end is not going to work as well. So this skeleton, through trial and error, you would find works the best. So that's step number 1. Step number 2 is to count our valence electrons. We have 2 hydrogen atoms, so that's 2 electrons. We have a carbon atom over in group 4, that's 4 more electrons. We have an oxygen atom in group 6, that's 6 more electrons. So we have a total of 12 electrons to work with. By the time you're done, your molecule had better have exactly 12 electrons. Think of it as the law of conservation of electrons. You can't lose them, you can't create new ones. You have exactly that number to work with, no more and no less. Step number 3 then is to place the remaining electrons in the molecule. If we look at it, we've used 2, 4, 6 electrons so far, which means we have 6 left. And we have 2 atoms that still need more. This oxygen still needs 6 more electrons to reach 8. This carbon still needs 2 more. Because oxygen is farther up to the right near our buddy fluorine, oxygen's pretty powerful, so we're going to give oxygen first dibs here. We'll take those 6 electrons and we'll give them to oxygen. And now oxygen says, hey, I feel pretty good. 2, 4, 6, 8. So oxygen's happy. Each hydrogen has 2. Hydrogen's happy. Carbon, not so happy. Carbon only has 6 valence electrons. What do you say we just put a pair of dots up here on carbon? That would be a very bad idea. If you did that, I'd have to walk up to you and say, did you count the electrons? Because you didn't. We can't put more dots in here. There are no more dots. So we're going to have to go to step number 4. And in step number 4, we're going to move a pair of electrons from the oxygen and make it bond out of it. So it's going to go from being a non-bonding pair of electrons to a bonding pair. If we do that, the oxygen still has its octet. That hasn't changed. But by sharing with carbon, now carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. And this is a perfectly good Lewis structure. This happens to be formaldehyde. Each atom has the right number of bonds. Each atom has its octet or duet. That's a perfectly good molecule. Next, let's take a look at silicon dioxide. Silicon being in group 4 wants 4 bonds, so clearly silicon will have to be in the middle, and that means oxygen will be on the ends. So this is the only really logical molecule we can come up with. To count the electrons, silicon would have 4 valence electrons. Each oxygen has 6, so that's a total of 12. That means we have 16 electrons to work with. Now we go to step 3, and that is to add our remaining electrons. We've used only 4 of our 16 to form the skeleton, so we have 12 electrons left, which is just enough to put 6 electrons on each oxygen. Now the oxygens are feeling pretty good. Silicon, however, is not so happy. The silicon atom only has 4 electrons. It needs 4 more. Well, anytime you need 2 electrons, that means you have to move a pair. So if you need 4 electrons, we're going to have to move 2 pairs. When we go to step 4, we're going to take a pair of non-bonding electrons from each oxygen and move them into the middle, and we'll form 2 double bonds to our silicon. And now the silicon has an octet. Both the oxygens have an octet, and everybody has the number of bonds they would like to have. That is a perfectly good molecule. One of the rules that you'll hear me say many times as we're doing these Lewis structures has to do with oxygen. And that is, never bond an oxygen to another oxygen atom unless absolutely necessary. Oxygen atoms don't like to share more than they have to, so they don't want to bond to another powerful atom like oxygen. In the case of ozone, O3, obviously we have no choice. We're going to have to bond the oxygens to each other. If there's no other way around it, by all means go ahead. But if it can be avoided, and you'll see in some of the upcoming examples that we can do that, don't bond them to each other unless you need to. To count the electrons, oxygen, of course, is in group 6, so each oxygen atom has 6 electrons, which gives us a total of 18 to work with. We've used 4 so far to make our 2 bonds, which means we have 14 electrons left. That's enough to put 6 on each end, and that leaves 2 for the oxygen in the center. The oxygens on the ends now have their octet. They are good. But the oxygen in the middle only has 2, 4, 6 electrons. It needs 2 more, and that means we'll have to move on to step 4. We'll need to take a pair of electrons from one of the ends, and it doesn't matter which one you choose, and move it into a bond, and that will now give our oxygen in the middle its octet. So the oxygen on the left has 2, 4, 6, 8. The one in the middle, 2, 4, 6, 8. And the one on the right side, 2, 4, 6, 8. That's a perfectly good molecule. Next, let's take a look at sulfur trioxide. And this will illustrate my rule about never bonding an oxygen to another oxygen. Sometimes people will just write the structure as SOOO, and we don't want to do that. Instead, we're going to put the sulfur in the middle and have each oxygen individually connected to it. Now you might be thinking that, wait a minute, sulfur is in group 6, it only wants to form 2 bonds, but it's got 3 bonds. The operative word there is wants to form only 2 bonds. Oxygen is a very powerful element, much like fluorine, and when fluorine and oxygen tell an atom to bond, they bond. So the sulfur, even though it doesn't want to form 3 bonds, it has no choice in this particular case. In the second step, of course, we'll count our electrons. So we have 6 electrons from our sulfur, another 18 from the 3 oxygen atoms, and that gives us a total of 24 electrons to work with. We've used 2, 4, 6 electrons to build our skeleton, and that means we have 18 left. And that's just enough to put 6 around each of our 3 oxygens. And if we do that, the oxygens are all happy. They've got their octet. The sulfur, however, only has 2, 4, 6 electrons. Sulfur needs to have 2 more. Once again, we'll have to go on to step number 4. We'll move a pair of electrons into a double bond, and it can come from any of the 3 oxygens. It doesn't matter which one. And that now gives sulfur 2, 4, 6, 8 electrons. Everybody has their octet, so even though they didn't get the number of bonds they would like to have, they all got the octet that they need to have. Similar to sulfur trioxide is the sulfite ion. The only difference is that the sulfide ion has a -2 charge. When you draw the Lewis structure of an ion, the 4 steps are exactly the same. It's only in step number 2 that we'll do something a little bit differently, and that is to take into account that charge. You may remember that a negative charge on an ion means that that ion has gained electrons. So a sulfite ion must have gained 2 electrons. When you do the count then, you're going to add up the electrons for the sulfur and the 3 oxygens and add an extra 2 for that negative charge. The skeleton is going to look the same as it did for sulfur trioxide. Again, oxygens don't want to bond to each other, so we're going to make sulfur form more bonds than it would actually like to. When we count the electrons then, we have 6 for the sulfur, 18 for the 3 oxygens, and another 2 for those 2 electrons in the -2 charge, and therefore this time we have 26 electrons to work with. We've used 2, 4, 6 electrons to make our skeleton. That means there are 20 remaining. That's enough electrons to put 6 on each oxygen, and it still leaves a leftover 2 for the sulfur. At this point, if you check the atoms, you'll see that each of those 4 atoms has an octet. Therefore, you do not want to go to step number 4. If we were to move a pair of electrons, say, from this oxygen into a double bond, the sulfur would now have 2, 4, 6, 8, 10 electrons. You don't want to have less than an octet, and you certainly don't want to have more than an octet. So we're done at this point, and our finished ion looks like this. They don't always have double or triple bonds, only if we need them. The reason I put the ion in brackets, this is a common thing we do when it's an ion rather than a neutral molecule. The -2 charge doesn't belong to any one particular atom in the ion, it belongs to all of them. So by putting it in brackets, we're showing that the -2 charge is distributed over that entire group of atoms. Next, let's take a look at hydrogen peroxide. We remember, of course, that oxygens do not like to bond to other oxygens if they can avoid it. However, we have a more stringent rule, and that is that hydrogen atoms can never form more than one bond, which means hydrogen atoms have to be on the end of the molecule. So in the case of hydrogen peroxide, the 2 oxygen atoms will have to bond to each other. Because oxygens don't like bonding to each other, molecules that have this in them tend to be unstable. Ozone, that we did a few minutes ago, is an unstable molecule. It tends to break down. Hydrogen peroxide is also unstable. That's why if you're one of those folks that likes to gargle with hydrogen peroxide, it makes your mouth foam and bubble, like you've got rabies or something. So in this case, however, there's no alternative. To count the electrons, the 2 hydrogens will bring us 2 electrons. The 2 oxygens bring us 12, which means we have a total of 14 electrons to work with. We've used 2, 4, 6 electrons so far, which means we have 8 left, which happens to be just enough to put 4 more on each of these 2 oxygens. And if we do that, the oxygens now have an octet. So the oxygens did get an octet. They got the number of bonds they would like to have. So other than having to bond to each other, it worked out pretty well. So that would be the molecular structure for hydrogen peroxide. Now, carbon monoxide's an interesting molecule. It's not going to follow some of the rules you're used to. But the skeleton is easy to do because with only 2 atoms, there's really no other choice than a C bonded to an O. If we count the electrons, carbon, of course, has 4, oxygen has 6, and that means we have a total of 10 electrons to work with. We've used 2 in our skeleton so far, which means we have 8 remaining. Since oxygen is stronger, we're going to give oxygen first priority, so we'll give oxygen 6 of those. and that leaves 2 more that we can put on the carbon. Oxygen now has an octet, but carbon only has a quartet. The carbon atom still needs 4 more electrons, and that means we're going to need to move 4 electrons from the oxygen and actually make a triple bond between the carbon and oxygen. This is a very unusual molecule. This is the only molecule you'll probably ever come across in which carbon has non-bonding electrons. Carbon, in 99.999% of the cases, will have 4 bonds, never dots. And for oxygen to have a triple bond, this is the only molecule I can think of in which oxygen actually has a triple bond. We had to do these things, however, because it's the only way that carbon and oxygen both got the octet that they have to have. Let's try a little larger molecule this time. C2H2O is an interesting molecule because there's actually more than one skeleton that will work for this molecule. When you can have more than one possibility, then that particular formula has what we call more than one isomer. Isomers are simply molecules that have the same chemical formula but a different skeleton or a different molecular structure. We're going to look at both of the possible isomers of this particular formula. One possibility, in fact, both possibilities, of course, will have one thing in common, or 2 things actually, and that is the carbons will have to be in the middle and the hydrogens will have to be on the ends. It turns out that oxygen can be in the middle or the end, and that's going to be the difference in our 2 formulas we talk about. If we count the electrons, the hydrogen atoms bring us 2 electrons. The 2 carbon atoms have 8 more. And the oxygen brings us 6. And that's a total of 16 electrons that we have to work with. We've used 2, 4, 6, 8 electrons so far, which means we have 8 remaining. We'll begin with oxygen. We're going to give oxygen 6 to get it to its octet, but we still have 2 electrons left, so we'll put those on one of the carbons. It doesn't matter which carbon you put it on. We'll just put it on this one on the end. The carbon on the end now here has 2, 4, 6, 8 electrons, and the oxygen also has 8. But this carbon in the middle only has 4. It needs 4 more electrons, which means we need to move 2 pairs and make extra bonds. So we're going to move a pair of electrons from the carbon on the end to the carbon in the middle. We'll move a pair of electrons from the oxygen to that same carbon, and that will form 2 double bonds to that central carbon, and now each of the atoms in the molecule has an octet. They also each have the number of bonds that they would like to have, so this is a perfectly reasonable molecule. Another possibility for a skeleton would be to take this hydrogen from the carbon and move it over and put it on the oxygen. If we do that, the carbons are still in the middle, the hydrogens are still on the end. We've simply moved oxygen from the outside to the inside, and of course oxygen is capable of doing either of those. It can have 2 single bonds in the interior or a double bond on the exterior. The electrons will still be the same, of course, that hasn't changed. And we'll still have 2, 4, 6, 8 electrons to build our skeleton, and we have 8 remaining. This time we're going to put 4 of those on the oxygen to get its octet, and that leaves 2 apiece for each of the carbons. Each carbon, of course, still needs 2 more. For this carbon to get 2 more, we'll have to move that pair into the middle. For this carbon to get 2 more, we'll have to move this pair into the middle. If we do that, then we're going to end up with a triple bond between the 2 carbons. So the carbons now each have 2, 4, 6, 8 electrons, the same with the oxygen. Each atom has got exactly the number of bonds it would like to have. This is also a perfectly reasonable structure. Both of these compounds exist. They're both perfectly stable compounds. They have completely different properties, because isomers tend to be very different from one another, but they do have the same chemical formula. The larger a molecule becomes, the more atoms you have, the more possible isomers there are. Just for example, if you had the molecule C40H82, there's 122 atoms in that formula. How many isomers do you suppose are possible for C40H82? It's actually 67 trillion possibilities. That's a lot of different molecules. Luckily, I'm not going to make you draw all those on a quiz or exam. It turns out that there's more to a molecule than just how the atoms are connected to one another and how many bonds there are between each of the atoms. It's also very important to know what the shape of the molecule is and what the angle is between the atoms in the molecule. A change in the angle between atoms can have a huge effect on the properties of a substance. A different angle or different shape of a molecule can turn a beneficial drug into a toxic poison. So it's important that we understand how to determine the shapes of molecules and what the angles are between them. There are just a few basic shapes and angles we'll have to deal with in Chem 3A, so let's start at the beginning. We'll take a simple molecule to begin with, CH4. If you sketch out the structure of CH4, the only way you can do it is to put a carbon in the middle and the hydrogens on the outside. Now, what is it that's connecting each hydrogen to the carbon? The answer, of course, is a pair of electrons. This bond between the two atoms is a pair of electrons. How do electrons feel about each other? They don't like each other very much. Electrons repel each other very strongly. So what determines the shape of a molecule and the angle is very simple. It's the repulsion between pairs of electrons which are attached to the atom in the center. They simply want to be as far away from each other as they can be. Now, how far apart are those pairs of electrons in this CH4 molecule? Well, it's probably pretty obvious that that is a 90-degree angle. So those pairs of electrons are 90 degrees apart from each other. Could we do better than that? Okay, could we put them farther apart than that? Well, possibly. This particular shape of a molecule is called a square planar shape. And because it's in the shape of a square and it's flat like a plane, it's that planar part that's getting us in trouble. We're thinking two-dimensionally when it comes to molecules. Chemists did that a lot in the past. In the 1800s, they would have assumed a molecule like CH4 would have been a flat plane, but somebody cleverly in the late 1800s decided to begin thinking in three dimensions. This is what CH4 actually looks like. The hydrogen atoms are spread out into three dimensions. The one thing that should be very obvious here is that angle is now greater than 90 degrees. 90 degrees would be here. That angle is clearly more than 90 degrees. And of course, that's going to be better for the molecule. The farther apart we can put those negative electrons from each other, the better they will like it. In this particular shape, the angle is 109.5 degrees. Now, that's probably not an angle you've ever heard of. I had never heard of it till I took chemistry in high school. 90 degrees, sure, we all learn in school about right angles. That's a pretty common one. But this angle, 109.5, is a geometric angle you're not probably used to seeing before. This particular shape of a molecule is called tetrahedral, and this shape is known as a tetrahedron. So tetra means four, just like it did back when we were naming covalent compounds. And hedron means face or side. If you connect any three of these hydrogen atoms, it makes a triangle, actually an equilateral triangle. So there's a triangle over here on the left, there's another triangle on the right, there's a triangle on the back, and there's a fourth triangle on the bottom. It's like 4 equilateral triangles put together, thus the name tetrahedron, and the shape is known as tetrahedral. Whenever you have 4 atoms attached to a central atom, it's always going to want to take a tetrahedral arrangement because it allows more space between those pairs of electrons. Let's take a look at a similar molecule, NH3 or ammonia. The ammonia molecule actually is similar to the CH4 or methane molecule because it has 4 things attached to the nitrogen. The difference is in ammonia there are 1, 2, 3 atoms, but the 4th position is a non-bonding pair of electrons. CH4 had 4 hydrogen atoms for a total of 4 groups, as we'll refer to them, and the ammonia molecule has 3 atoms and a pair of electrons, also which we would consider to be 4 groups. So whenever you have 4 groups attached to a central atom, whether they're all atoms or they're a blend of atoms and non-bonding electrons, we still have 4 pairs of electrons here trying to get away from each other. This particular molecule is referred to as a T-shaped molecule. When we talk about the shape of a molecule, we sort of pretend that the non-bonding electrons are invisible. We're really interested in the ball and stick part. So it's like this is the top of the T and that's the base of it there. Is this the best we can do? Clearly not, because once again we're thinking 2-dimensionally. If we think 3-dimensionally, once again it looks like we've got this shape based on a tetrahedron. We don't actually call it a tetrahedron anymore because when we talk about the shape of the molecule, again, we're only looking at the atoms, not the non-bonding electrons. But it's clearly based on a tetrahedron because we have 1, 2, 3, 4 groups attached to that nitrogen, and the farthest apart you can put 4 groups is 109.5 degrees. Now I should mention that the only time you ever get this exact 109.5 degrees is if all 4 of the groups are exactly the same. So when we had 4 hydrogens, it was 109.5. If I put 4 chlorine atoms, if each of these 4 was a chlorine, it would be 109.5. If I put a chlorine here with the 3 hydrogens, now the angle would be different by a little bit because the atoms wouldn't take up exactly the same amount of space. So in an ammonia molecule, it's actually about 107 degrees, but we're not going to worry about that. We're simply going to say that anytime there are 4 groups attached to a central atom, the angle is about 109.5 degrees. We don't actually call this a tetrahedral arrangement anymore because we don't really look at the non-bonding pair of electrons. It's known as a trigonal pyramid. The pyramid comes from the fact that we have a nitrogen at the top and 3 hydrogens at the base. So the base of our pyramid makes a triangle, thus the term trigonal pyramid. It's a bit different than an Egyptian pyramid. If you've seen a picture of an Egyptian pyramid, there are 4 points at the base. So an Egyptian pyramid is known as a square-based pyramid because there are 4 points at the base. We only have 3 here, so we refer to this as a trigonal pyramid. So once again, if you have 4 groups attached to the central atom, whether it's 4 atoms, we'll go back for a moment here, like we had with the methane, or if it's 3 atoms and a pair of electrons, it's still going to be 4 groups. It's still going to be a 109.5 degree angle. So with CH4, we had a tetrahedral arrangement. With NH3, we have a trigonal pyramid. Let's take a look now at the water molecule. Oxygen, of course, has to be in the middle and the hydrogens on the ends. So we end up with 2 hydrogen atoms attached to the oxygen and 2 non-bonding pairs of electrons to make up oxygen's octet. Once again, we have 1, 2, 3, 4 groups attached to the water molecule. The angle between the two hydrogen atoms is 180 degrees. But if you look at any two adjacent pairs of electrons, it's only 90 degrees. The distance between this non-bonding pair and the bond is 90 degrees. Same thing all the way around. So 90 degrees is the best that we're getting in this particular molecule. We refer to the water molecule in this particular shape as a linear molecule. Remember, when we're talking about the geometric shape of a molecule, we don't concern ourselves with those non-bonding electrons, we just look at the atoms. So the H, the O, and the H are in a perfectly straight line. That's a linear molecule. Of course, if we think three-dimensionally, once again, as we should, we can see that it takes on this sort of tetrahedral arrangement. At least it's based on a tetrahedron. So two of the points are hydrogen atoms and the other two are non-bonding pairs of electrons. In this particular shape for the water molecule, our angle is once again approximately 109.5 degrees. Of course, as we said before, it won't be exactly 109.5 because the non-bonding pairs of electrons and the hydrogen atoms don't take up exactly the same amount of space. I mentioned a little earlier that the shape of a molecule can have a dramatic impact on its properties. So this is what water really looks like. Water boils at 100 degrees Celsius. If the water molecule were truly a straight line instead of in this bent shape, we refer to this as a bent molecule because HOH is simply not a straight line. So if you're not a straight line with three atoms, then you're a bent molecule. If water were truly linear, then its boiling point would be about 150 degrees Celsius, which means that all of the water on Earth, even in Antarctica, would all be water vapor. There would be no liquid water, there would be no ice, because you would have to cool water down to below minus 150 degrees Celsius in order to turn it into liquid water, and life as we know it could not exist on Earth. Luckily for us, water molecules are actually bent due to the presence of those non-bonding electrons, so water boils at 100 degrees Celsius, which means at room temperature, water is a nice liquid. Let's take a look at some molecules now in which there aren't four groups. We'll begin with sulfur trioxide. With our rule, once again, that we don't want oxygens to bond to other oxygens, that means we're going to put the sulfur in the middle and attach the three oxygens to it. In this case, the angle between the three oxygens will be 90 degrees. So 90 degrees here, 90 degrees here. This particular type of molecule is a T-shaped molecule once again. Again, we have the top of the T here, and there's the stem of it. Is this the best we can do with our 1, 2, 3 groups? It turns out that it's not. We don't have to think three-dimensionally this time, but we can spread these things out. Think of the sulfur trioxide molecule as being inside a circle. If we divide a circle into thirds, 360 degrees divided into thirds would give us a 120 degree angle. That's certainly better than 90 degrees. This particular molecule is called a trigonal planar molecule. Trigonal because of the three groups attached to it, and planar because it's a flat molecule. You don't have to worry about three dimensions when there are only three groups. We only get molecules to be three-dimensional when there are four or more groups, and there are more than four sometimes. Normally, you won't get into examples of molecules with more than four groups until you get to general chemistry. However, a heads up, in question number 2 in experiment number 16 that you're going to be doing this week, there is an example of a molecule that goes beyond four groups. I just put that in there for a thinker. You know, I love to have a thinking question on each of the labs, and that's the one for this experiment. sulfur dioxide, a similar molecule. In this case, we have two oxygens attached to the sulfur, and there's a non-bonding pair of electrons, so it still adds up to 3 groups. This one, again, has that 90-degree angle between the oxygens, and we call this a bent molecule, because when there's only 3 atoms in a row, the 2 choices are linear or bent. That's the only thing you can have. Of course, once again, we can do better than this if we spread them out into this trigonal planar arrangement. We can now get a 120-degree angle between those oxygens. So this is what sulfur dioxide really looks like. It's still referred to as a bent molecule. Now, on quizzes and exams, I'm not going to ask you to tell me if a molecule is bent or trigonal planar or tetrahedral or whatever, for 2 reasons. Number 1, we've now seen that there are 2 different examples of bent molecules. Water molecules were bent, but it was 109.5 degrees. Sulfur dioxide is bent, and it's 120 degrees. So the term bent wouldn't be very specific. And the other thing that you're going to notice in a little while is when molecules get larger and there are more atoms, it's possible to have more than one angle in the same molecule. And I'm going to show you a couple of examples of that in just a little while. So when you're drawing a molecule, all I really need you to tell me is what are the bond angles. I don't need to know what that shape is, because if there's more than one bond angle, there's more than one shape, and so there really is no name for it. These shapes only work with very simple molecules. And finally, let's wrap up with carbon dioxide. Carbon dioxide has only 2 groups attached to the carbon. Remember, carbon never has non-bonding electrons. Carbon monoxide was our one exception. So the carbon has 2 atoms of oxygen and no non-bonding pairs of electrons. The farthest apart you can put 2 groups in a molecule is going to be 180 degrees. And this, of course, would be a linear molecule. Linear is an unequivocal term. Linear means a straight line. It means that it's going to have a 180-degree angle. Let's go ahead now and summarize everything we've talked about when it comes to the shapes and angles in our molecules. We started out with the example of having 4 atoms attached to a central atom. Whenever there are 4 groups, the farthest apart they can be is 109.5 degrees, and that's known as a tetrahedral molecule. Again, it's the angle that I'm most interested in. When you're doing a quiz, I don't need you to write down tetrahedral, but I will need you to write down the bond angle of 109.5 degrees. The second case we looked at was when we had 3 atoms and our non-bonding pair of electrons in ammonia. In that case, we had a trigonal pyramid. The angle is still approximately 109.5 degrees. Whenever there are 4 groups, our angle is going to be about 109.5. Same thing was true with our water molecule. We had 2 atoms of hydrogen, we had those 2 non-bonding pairs of electrons, and so 4 groups again gives us about 109.5 degrees, and this particular molecule is called a bent molecule. We then went on to examples of where there were only 3 groups. We started with sulfur trioxide, where there were 3 oxygen atoms hooked to our sulfur, and the farthest apart we could put 3 groups in a molecule is 120 degrees. And this is called a trigonal planar molecule because it's got 3 points and it's flat like a plane. The sulfur dioxide molecule also has that 120-degree angle because there are 2 oxygen atoms and that invisible non-bonding pair of electrons up here. The angle will still be approximately 120 degrees. And again, as I mentioned before, one of the reasons that these names are not so important, we have 2 molecules here that are both called bent, but the angle's not the same. That's why I'm much more interested that you can write down the correct angle rather than the name of the particular shape. And then finally, we finished up with carbon dioxide. Carbon dioxide only had two groups. There were two oxygens, but carbon has no non-bonding pairs of electrons. It almost never does. And so for two groups, the farthest apart we can put them is 180 degrees, and that makes it a linear molecule. Let's wrap up our discussion about the shapes and angles in molecules by taking a look at a couple of examples where there's more than one angle in the molecule. I had mentioned that previously, that we would talk about it. So let's go back and look at a couple of the molecules we drew earlier. This is one of them that we drew during our example problems. The thing you'll notice in here that there's 1, 2, 3 atoms in the interior of the molecule. Every atom that's on the inside in a molecule has an angle. This carbon is going to form an angle with the H and the C. This carbon is going to form an angle with the C and the O, and this oxygen is going to form an angle with the C and the H and the two non-bonding pairs of electrons. The carbon over on the left side is bonded to only two groups, an H and a C. Now you might be thinking, wait a minute, doesn't a triple bond count as three things? And the answer is no, it does not. Remember, the definition of a group is an atom or a non-bonding pair of electrons. The hydrogen is one atom, the carbon is one atom. So there's only two atoms hooked to that carbon. It has no non-bonding pairs. Two groups means 180. This carbon, same thing. It's hooked to an oxygen atom and a carbon atom, no pairs of electrons. It's also a 180-degree angle. The oxygen, however, is hooked to a C and an H and two non-bonding pairs of electrons. That's four groups attached to the oxygen, which means it's going to have to be a 109.5-degree angle. One of the very common mistakes that students make is they'll look at this oxygen and only look at the C and the H, and they'll say it's 180 degrees. Remember, those non-bonding pairs of electrons, they're important. They actually do count. Now, the other isomer that we did for this particular molecule, C2H2O, looked like this. In this molecule, there are only two internal atoms. This carbon is internal, and so is this carbon. So each of those is going to have an angle. If you look at the carbon over here on the left, it's attached to an H, and a C. That's a total of three groups, and therefore its angle ought to be 120 degrees, and it is. This carbon is attached to a C and an O, no non-bonding electrons, so it's got two groups. It would have to be 180 degrees. You can see why we don't use the shape names, because there's really no name for it. This part of the molecule is trigonal planar. This one's linear. What do we call it? Trigonal plilinear? There's no good name for it, so we simply label the angles. We have linear here and tetrahedral, two different shapes in the same molecule. We don't try to give it a name, we just label the angles. Now sometimes it's nice to see a more three-dimensional model of a molecule. This is what this molecule looks like. You can see that the H, the C, and the O are all in a perfectly straight line because each of these angles is a 180. And you can see the triple bond here in the middle between the two carbons. The oxygen, of course, is bent because there's a carbon and a hydrogen and the two non-bonding pairs of electrons. Those pairs of electrons push the hydrogen down so it's not in a straight line. Our other molecule, one end of the molecule, as we said, is trigonal planar. It's a perfect like Y shape here because this carbon is hooked to 1, 2, 3 groups. The other carbon is only hooked to two atoms. It forms a nice straight line, sort of like carbon dioxide did. One thing that's important to point out is the non-bonding electrons out here on the end of the oxygen, they don't matter because they're not part of the angle. Only non-bonding electrons that are on an internal atom actually affect the shape. The dots on the oxygen here, they're important because they are part of the groups that are attached to that central atom. This oxygen's on the end, therefore the non-bonding electrons on it don't really have any effect on the shape. They're just there. And that basically wraps up our discussion of molecular shapes and molecular angles.
Well, you've made it through the first 6 weeks of chemistry. We've just wrapped up chapter 12, which is all about covalent bonding and drawing the Lewis structures of various molecules. So in chapters 1 and 8, we focused on measurement and mathematical calculations. In chapters 2 and 11, we talked about the basic structure of the atom, followed by the more detailed electronic structures of atoms. And then we used that knowledge in chapters 3 and 12 to determine the formulas and structures of ionic and covalent compounds. So that essentially wraps up our first sort of unit of the course, and we'll have our first midterm exam covering those 6 chapters. So chapters 1, 8, 2, 11, 3, and 12.